Hey engineering students, welcome to the first video in week 7. So by now you should have your materials in hand, I'm hoping, whether it be your own stuff or some things from me. And you've got until the end of next week to submit your concept model. So all of that is outlined exactly what I'm expecting in an assignment on Google Drive, which should have launched this morning. I just want to emphasize again verbally though that I don't need this concept model to be perfect by any means. It's just meant to get you thinking about the project and what the solutions might be. It's meant to help you see any upcoming challenges, and it also gives us something that we can put in front of the client and just like help them to see what we're thinking, the kinds of things we're thinking, and then we all might spot something and say, oh, what about this? So we thought about this, or this would be, not what we thought. Here's another idea that could work. So it's kind of like physical brainstorming, I guess. And I'm hoping that just naturally some of you are going to choose the PathPoint project, and some of you are going to choose Mrs. Jones' Providence project. A lot of P's in there. So yeah, let's see how we go. Now, I also don't want you to forget about any of the forces or the vector stuff we've done. We're going to take a little bit of a break from it for this week and do something unrelated. I think I can safely call it unrelated, but we're going to go back to that. That's a huge foundation we're going to keep on building on along with everything else. And one other bit of housekeeping is that I've had one person have a Zoom appointment with me to do some extra work on the side, and well done to that one person. That is a huge secret to success. That is by no means a sign of weakness or anything that you should hesitate doing. It's no inconvenience to me. Remember, your parents are paying me to teach you, so it is no problem for you to reach out and make an appointment, and probably it's easier for you to tell me when you're available. My calendar is actually pretty free these days. I got plenty to do, but it's a little more flexible in the timing, whereas you have a class schedule. Okay, I think that's everything I wanted to go through. So this topic this week is it's all about area and centroids. And if you've already done the reading, or if you're going to do it after the video, you need to do one or the other. You have to read through. You would have seen all those words mentioned all through. So this is all about understanding two-dimensional geometry even better. Because I would say for a long time now in your schooling, you have been working with area. Like I look over my kids' shoulders as they're zooming right now. I would say my 4th grader is doing area calculations. I'm pretty sure I've seen that happen already. So, that you've been doing this for 4, 5, 6, 7 plus years. And you're very familiar with the idea of area. That's something you can do with two-dimensional figures. Something else you can do is find the perimeter. And that's kind of all you've done so far. Area is measured in square units, perimeters are measured in length units. But now we're going to look at something called centroid. All right, sounds like a weird alien kind of word, but it's incredibly important, very well understood engineering principle. For those students taking calculus, this is also intimately related to calculus integration, which is what you'll do in the 2nd semester. So I won't even bother explaining those things at this point, but we might circle back once you've learned how to do integration, and I'll show you how it matches up. So the centroid is basically, it's all about saying, if you have some two-dimensional area, whether it's random or it is, kind of like rectilinear is how we describe that, that there is some location where if you cut this thing out of cardboard, there is some location, let's say maybe it's right here, maybe it is right around here, and that if you really cut this physical thing out of a piece of paper, a piece of card, that you could either balance this on the point of a pencil right at that point. Okay, it's kind of like Very, very informal. Oops, I didn't like that. Extremely informal description, but it is kind of like a balancing point. Okay, here's my wooden pencil. Kind of, oops, I don't know what's happening there. You know, but like I could balance on the point of pencil, or I could poke a hole through it and hang it from a piece of string, and it would just balance very perfectly, very, very level at that point. Another maybe slightly more rigorous way to define it is that if you were, here I'll do it on the second shape, if you were to split it with a vertical line and also a horizontal line, like right through that centroid, that you would have exactly the same amount of area above and below, left and right. All right, let me explain what I mean. So firstly, above and below. So like that, if you split that centroid just like I have with those kind of axes, that I could take all of the area above, and what do I need? I need another color, don't I? And you could take all of the area below, and that the green area would be exactly equal to the purple area. And then likewise, that if you split it on the left-hand side of that centroid and on the right-hand side of that centroid, that the exact same thing would be true. Okay, that the green area is equal to the purple area. All right, that's, as I say, kind of a slightly more rigorous definition of what the centroid means. It is a balancing point. It's where you've got the same area on both sides of that middle. Okay, and maybe a term which you're maybe slightly more familiar with would be the word center of gravity. Okay, anyone who's like, you know, tried to balance or done like physics balancing acts or anything like that is, you know, at least a little bit familiar with the idea of center of gravity. It's actually where, like, you know, if you have a solid object, here's one of our, you know, little ubiquitous boxes that we always draw. If you have a solid object, that there is a particular location called the center of gravity, and that location is actually where the weight force acts. All right, so it's like a balancing point. It's how you know if something is going to balance. If you have a let's see, like a little square stool. Okay, here's a little stool, 4 legs, 1 leg is behind, it's hard to see. And then if you could find the center of gravity, that's where the weight force acts. And so as long as that weight force is directly above the support area, it's not going to fall over. All right, but if you can imagine like some object which, you know, this will be kind of a silly object which would never really be probably created in real life, but imagine like a solid object here and the center of gravity was like here, the weight force punching down through it. See how it's not supported by that support area, so that thing is going to fall over. Okay, so all of these are very related ideas. The centroid for 2D shapes, the center of gravity for physical mass objects, and the weight force that acts through them. And we've been talking, of course, about mass and weight and density already. So that's one reason why the centroid is an important topic to understand. It does connect in with where the weight is applied to an object. And then there's another application later on too, if we get to that, in the second semester, to do with bending beams and things. Now, if you read in the textbook, I got my textbook right here with me, on page 136, it mentions there are 2 sort of types of regions. There are discrete regions. Okay, now that is not It's not the same as when you are being discrete, like you're being secretive or being subtle. This is spelt R-E-T-E, and it simply means like it means bounded, like something that has boundaries. So they mention a discrete region and they mention a continuous region. We are really only going to deal with the discrete region. The continuous region, as I said earlier, it is connected to calculus. You need calculus integration to solve the problem. They do actually go into it in this book. Calc students, if you want to circle back to this in about 3 or 4 months, you can do that. But for now, we're just going to do discrete. It's far easier, and we can do it with simply like basic algebraic skills. Okay. So let's get into following along with what the textbook says. I'm going to kind of jump right now to page 138. So if you go to that, you'll be most equipped to understand what we're doing here. Okay, page 138. I'm not going to give any different or other kind of information. I'm just going to sort of walk through and explain, because there's a lot of diagrams, a lot of numbers, and I want to make sure that you get it. So, first of all, we start off with shapes that are simple rectangles. Now, it is very fortunate that rectangles are actually very, very common. You know, I look around the room that I'm in right now, and actually there's a ton of rectangles everywhere. The door is a rectangle. That little window pane right there is a rectangle. Rectangles are absolutely everywhere, so that's good because they're also really easy to understand. So the first thing that we do, and this is very important, I'm going to use blue for this in every example. First thing we need to do is we must set up an axis coordinate system that has an origin. So I'm going to use that blue dot is the origin. I'm purely copying this bit by bit, step by step, the diagram on page 138. Okay, that's the origin, and this is just simply our good old friend, the x-axis and the y-axis. So this is starts with a C, a Cartesian plane. Okay, we're putting a shape onto a set of x, y axes, and I've said this before, but it's called a Cartesian plane because René Descartes, French mathematician, was really the first person to meld geometry and algebraic graphs together. So he gets the honor. Now let's give some labels here. I don't think it'll come as any surprise to you that every rectangle has a base and a height. Okay, and I will only use the arrows. You can see on page 138, they do use arrows to show exactly what length we're talking about. I will do that when it is possibly ambiguous, like when it could be interpreted either way. If it is absolutely abundantly clear, as I think it is in this case, what B and H refer to, I won't bother because it just clutters up the diagram. Now, area. If you don't know that the area of a rectangle is base times height, then you might have some problems. That is something that, as I say, I have seen my 4th grader doing. It's the very first area calculation that anyone ever encounters because it's so straightforward. Area is base times height. Also note, I don't put the parentheses around the H because I don't think they're necessary. And he doesn't use them in the other ones around H, so I think it's inconsistent. We always use exactly what we need and nothing more if we can help it. And then he talks about the centroid location. So I think the centroid of a rectangle is extremely intuitively, if that is a word, obvious. It's the balancing point. It's like the dead center. It's where, as I said, where the area on the left and the right, or above and below, well, both of those actually, is the same. And one little help, which you should always keep in mind, just in my gold or brown pen, is always look for symmetry. If symmetry ever exists in a shape, the centroid will always be on that line of symmetry. Always. No exceptions. Okay? I'll say that again because it's so important. If you are presented with a shape that has a line of symmetry, then the centroid must be on that line of symmetry. So, that could go, you might have a shape that is kind of complex, but, oops, not at the end there, it didn't. But you can see what I'm doing here. That arrow does have a line of symmetry down the middle. So that means the centroid will be somewhere on that line of symmetry. Now you still got to work out exactly where, but I think you get the gist, okay? That it's somewhere on that. So we can easily see that the rectangle symmetry, I'm not even going to sketch it in because then I just got to erase it, but it's extremely obvious. I'll use green. The centroid is right there, and I will do what the book says. I will use a C for centroid. And let's see. Oh, sorry, I want to use exactly the same terminology. Okay, so they are using X. Is that a 1? I can't tell if that is a 1 or a vertical line. Or is it an I? Wow, that's hard to see. Okay, it looks like it's a 1. If I had to guess, I think it's a 1. Nope, it's an I. Nope, I can see one of them now. It is actually an I. Sorry about that. I was only really glancing at it before, and I didn't think I need to really use that. Okay, so what we're saying is that this distance, and the distance is, it's very important to note, we're saying the distance in from the y-axis. We're calling that xi. And then we're calling the distance up from the x-axis, we're calling that yi. So really, another way to put this is that we could say the coordinates of the centroid are xi, comma, yi. And you will see why we can use the i's. Maybe not this lesson, but definitely next video. So the centroid location for a rectangle, once you have set up this blue coordinate system, okay, you can't really talk about these dimensions until you create the coordinate system, but the x distance is going to be half of b, which is b over 2, and the y coordinate is going to be h over 2. Okay, half of h, half of b. So, let's just give you a quick little example here. I don't know if you really even need it, but let's do it. So if you have a rectangle which is like 10 and let's say 6, as long as you have defined an xy coordinate system, then you can pretty confidently say that the x location is half of b, the base, the 10 over 2, 5, and oops, and the y coordinate is h over 2. H is the 6, the height. 6 over 2 is 3. So that means our green, I'm going to keep using green, our green centroid has coordinates of 5, 3. Okay, so there's like more letters and more terminology going on here than are actually necessary to understand this for a basic rectangle, but with more complex shapes you are actually going to be glad for this. We're building a more elaborate framework so that we can build something a little taller, all right, a little more complex ultimately. So yeah, I hope that makes sense to you. If not, you can always rewind, watch again, or keep watching the next shapes I do, or you can also reach out and ask me. Let's do another shape. Let's do the triangle. We like triangles, we've seen quite a lot of them. This time I'm just going to do my X and Y first. And again, I'm going to exactly do what the book is doing. Okay. Actually, you know what? I know it's coming up, so I'm going to make life a little easier for myself. Okay. And again, we have a base and we have a height for our triangle. And again, we have an origin, which is just like the intersection of the X and Y axes. All right, if you don't know the area of a triangle, it is half base times height. Again, that is one you should absolutely know from memory. The justification for that is pretty simple. We're just saying that if you could imagine that this were actually a full rectangle, then its area would be base times height, and it's clearly only half of that rectangle. That's the reasoning. Half base times height. And now the centroid here is not actually quite as obvious or intuitive as for the rectangle. Maybe some of you have done this exercise before, where you find the median of each side length, okay, like the halfway point on each side, and then you draw a line to the opposite vertex. I didn't do that very well. And they meet somewhere in the middle, and that is the balancing point. Anyone ever done that before? That's kind of a common little fun thing you often do in 9th or 10th grade geometry. That will also yield you the centroid, but it's actually a little more complex mathematically than what I'm about to show you, just even easier. And there's no surprise, it's right there in the book. Whoops. So we are going to put it in. It's going to be right here. And the way that works is xi, which remember is this distance, okay, the distance across the x coordinate of the dot, the centroid dot. Oops, I was going to label those, wasn't I? This is always going to be 2/3 of the base. 2/3 of the distance along. That's why I redrew it to make it exactly 6 units, so that the 2/3 would be exactly 4 units. And then that distance, yi, the distance up, that is 1/3 of the height. One little comment that I'd put here is that it's probably actually easier. I'm just going to do this in parentheses here. It's probably easier if you just always think of it as being 1/3 in from the thick end. I think that's easier, because then it's like 1/3 and 1/3. You know, if I were instead coming in from the thick end, then it's 1/3, not 2/3. I want you to think that it's like, when is it 2/3? When is it 1/3? It's always 1/3 from the thick end, or conversely 2/3 in from the pointy end. You know, I just as easily could have drawn this triangle going the other way up, but I'm trying to match to what the textbook is doing. And in that case, it would have been exactly 1/3 of the height and 1/3 of the base. They would have been the same thing. So don't get too confused with just trying to memorize formulas. Always try to see what's really going on behind the formula, as it were. It's 1/3 in from the thick end, or 2/3 in from the sharp end. Oops, I'm gonna erase that. All right, we've got area, we've got that. Okay, and by the way, for this triangle, because my base is 6 units, reading off just, judging by grid squares, 2/3 of 6 is 4, 1/3 of 3 is 1. So I have coordinates of 4, 1. And remember, I'll say it again, those coordinates only make sense because I first set up an XY axis with an origin. If I just have a triangle floating around in space, it's much harder for me to say, oh yeah, here's the centroid and its coordinates are, 2, 1, because you're not referring back to anything. The triangle's floating around in space, so are these my XY axes? Is this my XY axis? Is it aligned with the triangle base? Is it aligned with the room that I'm sitting in? No one really knows. So you have to set up those coordinate axes first. Okay, let's do the circle. Circles are very crucial. We find them all the time. All right, axes. And if you are not taking notes, you should be. Absolutely be doing it. This is going to be one of the world's worst circles. I've heard a legend, was it Michelangelo was supposed to be like the test of whether he was going to be the guy who got to paint the Sistine Chapel. He had to be able to draw the most perfect circle out of the bunch, and he was able to do it. It is not easy. It's much easier when you do ink to shape. Look at that. Oh, it's incredible. I've actually turned that off because it keeps on messing with what I'm doing. Anyway, the area of a circle is always pi r squared. They do add in the other formula, the other one. I don't like it much at all. Oh, sorry. I do not like that, Sam, I am, because, I don't know, what you'll find in math and science and engineering is that the radius is actually the fundamental descriptor of any circle, not the diameter. The diameter is actually kind of derived. It's downstream of the radius. A circle is defined by the set of all points at a given radius from a given center. Yeah, the diameter is kind of a secondary thing. So I will slightly change his diagram. I would rather say here's your radius. We still have a center, and as it happens for the circle, again, this one's very intuitive. It's always going to be that. Easy, right? But this also gives me a chance to say, this is why setting up coordinate points, a coordinate axis system, is so crucial, because there is absolutely no reason why you couldn't draw the same circle, a little better that time maybe, and like what if your XY axes were done like that? They can be, if you want them to be. It's up to you. In that case, we know where the centroid is. It's right here. But in that case, I would be more correct to say that that was true. Okay? That distance was actually the radius. Which in this case, it looks like it's 2, 2. Okay? Now, don't write that one down. I'm just trying to point out that everything is connected to how you define your coordinate system. So it is vital that you set that it makes sense, that it's going to work for you, but that once you set it, you stick to it. Okay, you're going to find this more and more as we go. All right. The other one there, I'm actually going to skip the parabolic area. I'm going to skip the half parabolic area. I'm going to skip the half parabolic complement. those we won't really do. The quarter circle is there. I think you should write that down as well. The method is the same. You set the axes, set that origin, and then because it's a quarter of a circle, that's why it's pi r squared over 4. Okay, that's pi r squared. You know, this one right here, a full circle divided by 4. And then, you know, those little xi, yi, they're obviously a little more complex. I'm just going to tell you right now, I'm not going to include those last 3 on the assessment for this week for either grade level, either difficulty level. So they're important, but keep it as a reference in this book. Now, let's rewind a little bit. What about areas that don't fit those, that aren't squares, rectangles, triangles of any sort, circles, half circles, quarter circles, parabolic shapes, complements of parabolic shapes? What about those? So, you know, like you might have, well, I guess let me show it to you again. I showed you that like arrow shape. Let's just start with area. Forget centroid for a second. How do you find the area of a shape like that? I hope that the answer would come pretty simply to you, that you would say, oh, well, Mr. Meath, what we got to do is we got to split it up. And by the way, this, if you didn't hear me say that, this is a composite or composite shape. It's composed of different subshapes. So the first thing to do is we say, well, we got to split that thing. And there's usually multiple options as to how you could split something. It doesn't really matter. Choose whatever is going to work in your favor and keep it simple. This would be the simplest way that I can see. And you would say, oh, well, now we know, here, let's just label those lengths as per the grid squares. We would say, oh, right. Well, the total area is going to be the area of shape 1 plus the area of shape 2. And this is why we're using those i's before. Remember, i's are like little counting numbers, like little placeholders. So this means that we can use them to like number off, to count off as many sub-shapes as we need. Okay. And so in this case, the area of shape A would be, it's a triangle, so half base times height. Area of shape 2 is a rectangle, so BH. All right. Triangle area plus rectangle area. The base in this case is a 4. The height in this case for the triangle is a 3. For the rectangle shape 2, the base is a 2. The height is a 3. You do the math. Half, you know what, let me just do it all at once. 6 plus 6, and you get 12. No units were given. It's nice if you write units squared, but when no units are given, it is acceptable, I would say, to leave off units altogether. So yeah, that's your basic plan for doing composite shapes. It's also possible to do negative area for composite shapes or composite shapes. You might have a rectangle that has, well, you know what, let's do this. Maybe you're making some kind of complex woodworking shape, and you have a rectangle. So the area I'm talking about, if it's not clear, is this part right here, and that's been cut out like a circular or a half circular cutout. So what you would do in this case, you would say, well, my total area is still going to be, let's say, shape 1, but now we're going to say minus shape 2. And by shape 1, let's put these links in. By shape 1, I'm referring to the overall rectangle. By shape 2, I'm referring to a half circle. Okay, the half circle in this case is like a negative area. We're taking it away from the bigger picture. So let's see. Rectangles we know are base times height. Half circles are pi r squared. We already mentioned that. But half of that. Or if you prefer, you can do it over 2, on 2. Base in this case is the 4, the height is the 5. Okay, that's just like the full rectangle, all of it. Pretend the cutout's not there. And then we take away half times pi times what is the radius here? You should call it out, make a choice. It's 2. It's not the full 4. It's like, imagine here's the center of the circle. Here is that radius of 2. All right, half of the 4. So we got 20 minus 2 squares 4 over 2. 20 minus 2 pi. And when we're doing physical area calculations, please actually do it as a messy decimal. I don't need things to be in terms of pi when I'm gonna go to my woodworking shop and cut it out of wood. That doesn't help me. What does help me is to know that it's 13.7 as I say, units squared, whatever those units might be, centimeters, inches, feet. Okay, 20 minus 2 pi gives me 13.7. Pi is on your calculator for sure. If you can't find it, you could use like 3.1415. Just in the meantime, that'll give you more than enough precision. All right, now I'm going to, we have about 20 minutes left in this video. I don't think we're going to use all of it, but I'm going to switch tack. I'm going to give you a little quick ad break on something to kind of get your creative juices flowing. And then I'm going to show you some other tools that we can use to do this. So hold on while I switch the camera. Alright, let's switch over to some images. This is just a little ad break for you to try to inspire you with a very relevant project to the ones that we are doing with PathPoint and Providence. Give you a little background, we have been meeting outdoors at our church for about 3 months now. And we are under a great big tent, and we have the worship and the preaching, and we're all spaced out in our own little family squares. It's going really well, but one thing that we're not quite used to is that we have our kids with us during the service for pretty much the whole time. And you know, that is not how a typical American church runs, for good or for bad. So we're trying to think, how can we get our 4 little rambunctious boys to sit a little more in their place and you know, not be distracted or distracting, but be fully engaged. So one idea I had was, why don't I build them some little personalized folding wooden chairs? You know, kind of like that preschool idea that when you're sitting on your mat, like that's where you stay, and it's a very clearly defined boundary. So I thought it'd be fun to do that, as well as give me a little more experience in making some more furniture that moves and folds and has multiple configurations, because that is what we're doing for both of our 2 projects. So this is like akin to the sketches that I want you to produce for your first concept. You can see it is fully annotated. That means it has all the notes all over it. And those notes refer to things like what material it's made out of, how it folds up, you know, its different configurations. I've got some exploded view. That's where it has the legs inserted here. And those are not like in the diagram where they would be, but they're shown like off to the side so you can see the rest of it without any obstruction. I've got some comments about critical design elements like the bolts for the hinges, where it rotates, how the slats match up, things like that. I got basic dimensions. You can see 18 inches. You can't actually see it right now, but it says 12 inches as well in the other direction. And I think I attached this to the assignment as an example for you. But yeah, this was all I needed to be able to go ahead with my design. I also made an Onshape 3D CAD model, which was, of course, had all the the mate connectors to make it fold and change and everything. It's pretty cool. But anyway, I went ahead and I built it, and it looks like this. That's the folded configuration right there, and that is what it looks like all set up and created. Okay, I was very happy with how it's turned out. It's perfect size for a kid. You can actually sit in it as an adult as well. I made the first one, that's Orion there, my 5-year-old, and I think I'll make an identical one for my 7-year-old too, and then we should be all sorted with the other chairs that we have. And it wasn't perfect, but I think my next one will be a touch better, and I learned a lot, and I think I'm even more ready to help you guys out with the one that we're going to be doing for Pathpoint and for Providence. Ad break is finished. Now, before we finish up this this day's lesson, I want to also show you a really cool method which I hope that you will adopt. In fact, I don't just hope you'll adopt it, I'm requiring it on your assignment this week. I'm doing this because I want to teach you how to use spreadsheets. Older students who got more experience with this, I want to bring everyone into the fold. Spreadsheets are a very high quality way to try to catch errors in your working, make you more efficient over time, and they're just really cool. So here are the two composite area calculations that we just did, just kind of by hand in our just sketches. So I'm just going to keep those two examples so we don't bring any new aspects into the mix. This is also going to match pretty well to the table of calculations which appears in the textbook reading for the more complex shape that you see in there. I don't recall exactly which page it is, but it's the one that has like the triangles sitting on the block with like a hole in the middle of it. And we're going to tackle that and only that in the next video. I'm going to walk through that step by step. So this will give like a little bit of a lead up to that and just teach you some basic spreadsheeting for those who don't know how that works. So let's start with this first one. So we're creating a table. So we're going to say, what did I call it? Like, let's say which sub-shape. Our textbook also uses the word region a whole lot, which I like. Region's a great word. A little more vague and inclusive. Sub-shape. So we're going to say like shape 1, shape 2. And that is our list of them. Obviously there could be many more, and you can refer to them in different ways. Shape A, shape B, you know, Sally, Freddie, George, whatever you like. What I would recommend you do is you actually write in the critical dimensions of those shapes. Like I would say, why don't you actually write in what the bases and heights are of these particular shapes. So shape 1, you know, I might even point out here, this is a triangle. That just helps us keep track of it. Shape 2 is a rectangle. In spreadsheets, this is whether Google Sheets or Excel, if you double click, see this little blue area? I'm hovering right here on the right hand of column D. If you double click that, it makes the column match to the words that are in it, which is what I want right now. Base dimensions, okay. And also, what we can't do, we can't put like, you know, 4 inches. We can't put the word inches into a cell here because we're going to use that cell for calculations, as you'll see. So have pure numbers, and if you want to put dimensions weren't given, but let's say it's centimeters. It's better practice to put those in the column headings. All right. Shape 2 was a rectangle. The base dimension is 2. The height of the triangle, shape 1, is 3. And the height of the rectangle is also 3. And a little bit of formatting now. I'm going to make my headings in bold, and I'm also going to give them a little bit of color in the old cheeks. And I'm also going to center. Look at that. It doesn't take much, and it really cleans up what you're looking at and makes it a lot easier to work with. You can also play around with like, you know, borders if you wanted to. You know, you could do borders. Some people like that. You can even turn off grid lines and just have the table. That's actually a nice clean way to do things. And I might make that a bit shorter and just pull it up. There we go. Doesn't take a lot, like I say. And you know, I'm going to center my column headings as well. All right. Now I'm going to do the area. Notice the way that I show superscripts. What that means is centimeters to the power of 2. That is called a carat, spelled C-A-R-A-T. Okay, and it's found by doing Shift 6 on the keyboard. Another way you can do that, it's also acceptable, I think, just to write CM2, and everyone knows what you mean, although it's not, strictly speaking, very accurate. But yeah, visually it looks a little better. I believe it is possible to, if you select the 2 and you go, does it exist? Does it exist? You know what? It might not be possible. Okay. If you're working in Microsoft Excel, you are able to just select a piece of the text and turn it into a superscript. It looks like you can't do it in here. All right. Now we get to the area. Now, for those who are not used to spreadsheets, this is where the magic begins. Because do you think that I'm going to type in 6 because 6 is half base times height? Half 4 times 3? No, I am not. I'm going to start a formula. You don't have to write that. I'm just sort of doing like subtitles as I talk here. You know a formula. And formulas always start with an equal sign. That is how you begin them. So what you do is you click on the cell, you press the equals, you press the equals sign, all right, and that is the signal to Excel or Google Sheets or Numbers is the Mac version, that you are about to create a live calculation cell. All right, ready for it? So what's the formula for triangle area? Well, it is half base times height. So I'm going to do 0.5 for the half. I'm going to do an asterisk. Okay, asterisk is above the number 8 on the keyboard. 0.5 times, that's how we do times, not with an X, times the base. Now, what is the base? Well, it's that 4. But I'm not going to type the number 4. I could do that. I could do 0.5 times 4 times 3. And then I can press enter and I get my 6. But it's even better. You spreadsheet people know this. 0.5 times, and then I simply click once on that particular cell. And now it says E3. E3 is the column row reference. That's my base times height. I click here. There it is. F3, column F, row 3. So it looks a little weirder right now. 0.5 times E3 times F3. But what that means is 0.5 half times the base times the height. I press enter. I still get my number 6. But here's what happens. Let's say that someone comes back to me and says, oh, you know what? We have this design, but we changed it. The base is now going to be 5, not 4 centimeters. I type 5 instead of 4. And I press enter to update everything. And look at that. My area just automatically now is 7.5 because it still is referring to half of whatever that number is times half of whatever that number is. I'll put it back to how it was, 4. But that is just the coolest thing about spreadsheets. Let me copy my formatting over. Here's how you do that. You select the cells that you want to be the template. You click once on this paint format, and then you drag across the cells where you want that, and it makes them exactly the same. That was cool. Let me show you that again. You select where you want the formatting to be copied from. You click once on Paint Format, and then you drag, select, paint it in. All right, area of a rectangle equals, I start a formula. Ooh, look at that, suggesting. Yeah, I don't actually want their suggestion, but that's fine. They're suggesting a triangle formula. I don't want that. I want a rectangle. Rectangles are base times height. So I'm going to do equals base asterisk F4 for the height equals 6. As it happens, they are the same. That's coincidence. That's not normally the case. Okay. Now what I would do in this case, I might do a separate line here. I'm going to say, what are the totals of things that are happening here? Really what I care about is the total area, but when we get to the centroid and other stuff, there'll be other totals, but I'm gonna, let's see, I'll use that. Now, I want the total area, and again, I could just type in the number 12 because it's really obvious, and I want that centered. I could type in 12, but then if this thing changes again, that doesn't update my total, does it? So, spreadsheet people, you know where I'm going with this. I'm going to put in a formula instead, and there's two ways I could do this. I press equals. I can either do this cell plus this cell equals 12. That's one way to do it. Click on the cells you want with pluses, or I can type the word sum, which sums a series of numbers or cells, open parentheses. You get a lot of stuff here. It's trying to help you. It's going to be overwhelming at first, but it's trying to help you. Sum, open parentheses, and then just kind of drag select over the cells that I want summed. That is called an array in spreadsheets. That's an array from G3 to G4. Notice the colon in between them. Close my parentheses, enter, I get 12. Okay, that was called an array. There it is again for you to see. Sum, open parentheses, G3 to G4. I got that simply by drag selecting. You can also type those arrays manually. And notice in Google Sheets, it actually gives me a little preview of what the answer is going to be before I even press enter, 12. And that can help with debugging. Look at that. Total is 12. You know what? I'm going to change it. I'm going to put this right here. And I'm going to call it total area, because that's all we're doing today, is just the total area. Excellent. We got another one over here, and what I'm actually going to do, I'm going to grab my cells that I already did because I worked so hard on them. I'm going to do Control C for copy, Control V to paste. Okay, let me subtitle myself again. Control C for copy and Control V for paste. If you are on a Mac, that is Command C for copy, Command V for paste. Command is the weird squiggly, looks like a hairball, looks like pig pens, cloud of dust from Peanuts, you know. Now all I got to do is update a few things here. Shape 1 in this case is actually the rectangle, we said. Shape 2 was the half circle. I might just double click here to make sure I'm getting everything. Now in this case, I don't really have a base and a height, so what could I do? I mean, there's other ways I could do this to make it consistent. I could say like dimension 1, dimension 2. It's not a very exciting word, not very specific, but it still is accurate for the rectangle. And then for the half circle, dimension 1 is 2, and there just is no dimension. Sorry, did I say that right? Dimension 1 is 2, that's the radius, and there is no dimension 2 because a circle is fully defined by its radius alone. So I just don't have a number there, I don't need a number. I want to look at my formulas here now. This is a rectangle, so that should not be half times base times height, it should just be base times height. Just like that. For half circles, we had this on the sketches we were doing earlier. If you remember it, if you have your notes, it is half times radius squared. So here we go. Half times Oh, I'm sorry, half times pi times radius squared. Now the way you do pi in spreadsheets is you type pi, and I think that is actually it. Half times pi times radius squared. It used to be in Excel you had to type pi, then open close parentheses. We'll see if this works. Okay, this says half pi times radius squared. Notice that caret there for the squaring. I guess instead of that, I could have actually also done times E17. You could do it twice. That's what squaring is. That's another way. Both work. Okay, looks like looks like it is exactly the same as Excel. You have to do pi, then open close parentheses. This is how you show pi. Pi, open close, that's it. Don't ask me why. It's actually because pi is a function, really. It's a constant function, but that's okay. Now we get all these delightful numbers. Did we do the half? We did. Yep, half pi radius squared. Okay. Now, there's a little too much precision there for my liking, so I'm going to go up to my buttons right up here. And I'm going to decrease the decimal places till it looks a little more like the kinds of numbers that we care about. Notice that all the detail is still there, more than you'd possibly ever want. And there is no diminishing of precision, accuracy as you perform successive operations, unlike doing it by hand. Also down here, I don't actually think we need that much. So total area in this case is 18.3, except there's one problem. Because I copied this over, it is still adding the 12 to the 6.3. Why is that a problem? It's a problem because the half circle is a negative area, so it must be subtracted. So the sum function is no longer going to do us any good, so I'm going to get rid of it. We're going to say the full rectangle minus the half circle. There it is. Total area 5.7, exactly the same as we got with our hand calculations. We are all good to go. Look at that beautiful little spreadsheet. I want you to learn this yourself because you got to do it this week. That is your assignment. You're going to be doing it in Google Sheets. You're going to attach it to your Google Classroom assignment, and you're going to click on Turn In. But there's going to be more to come as well. More to come regarding Centroids, but this is a great example for you. Rewatch the video if you need more help. This was only about 17 minutes worth, and that's where we're going to finish it. Thanks for all your attention, and we'll see you again on the next video. Adios.